Here in section 7.6, I want to talk about Lagrange multipliers, which are all about optimization of multivariable problems subject to some constraint. Lagrange multipliers is named after Joseph Louis Lagrange, pictured here, who came up with this method in the 1700s. So here's how the method works. If we have a function f of xy that has a minimum or a maximum subject to the constraint g of xy equals 0, then that maximum or minimum will occur at one of the critical points of the function capital F, defined by capital F of x, y, and lambda equals lowercase f of xy minus lambda times g of xy. Here, lambda is called a Lagrange multiplier, and to find the minimum or maximum of f, here's what we do. 1. We solve the following system of equations. The partial derivative of capital F with respect to x equals 0, the partial derivative of capital F with respect to y equals 0, and the partial derivative of capital F with respect to lambda equals 0. Once we solve that, we'll have our point xy, or our multiple points xy, and we evaluate that lowercase f function that we had at the very beginning at each solution to that system of equations that we got in the first step. The greatest value yields the maximum of f, and the smallest value yields the minimum of f, subject to the constraint g of xy equals 0. So that may sound like a lot, but it's very similar to something we did earlier in the semester, optimization problems. In fact, let's take a look at one of the optimization problems we did on our most recent exam and see how Lagrange multipliers can help us solve it. So here we have an animal shelter has 160 feet of fencing to enclose 2 adjacent rectangular playpen areas for dogs. See the image below. What dimension should be used so that the enclosed area is maximized? So we want to maximize area. Here area will be our lowercase f, and it will be given by 2x times y, because the area of the entire rectangle is 2x times y. What is the constraint that we're subject to? Like we did in our exam, the constraint is 4x plus 3y equals 160. Okay? But remember that in this Lagrange multiplier method, the constraint has to be some g of xy equals 0. So with that in mind, is there any way to rewrite this to be some sort of g of xy equals 0? Well, yeah. If we let g of x comma y equal 4x plus 3y minus 160, then g of xy would equal 0 at the particular x and y's. Okay, with that in mind, our capital F function of x, y, lambda will be f of xy minus lambda times g of xy. Okay, and we can work this out to be 2xy minus lambda times 4x plus 3y minus 160. And this expands out to be 2xy minus 4 lambda x minus 3 lambda y plus 160 lambda. And so now we take our partial derivatives. We get fx, the partial derivative with respect to x of this guy here, is 2y minus 4 lambda. We're going to set that equal to 0. Fy, the partial derivative with respect to y, we'll get 2x minus 3 lambda. We're going to set that equal to 0. And then f lambda is, and here's a fun fact that can save you all some time. When we're taking the partial derivative with respect to lambda, it's going to be easier to take it of this function here. Now again, they're the same functions, they're just written differently. But written in this format, in order to take the partial derivative with respect to lambda, well, 2xy is a constant, so we ignore that, it goes to 0. And so now we have 4x plus 3y minus 160, which again is just a constant in terms of lambda, multiplied by lambda, or I guess in this case minus lambda. And so all we're going to get is negative 4x plus 3y minus 160, and we're going to set that all equal to 0. So let me rewrite that as minus 4x minus 3y plus 160, and again we're going to set that equal to 0. And now we have a system of multiple equations, and we can solve it with substitution. So here, this equation, if we add 4 lambda to both sides and divide by 2, we get y equals 2 lambda. And similarly, adding 3 lambda to both sides and dividing by 2, we get x equals 3/2 lambda. And then here in this bottom guy, if we plug in lambda for everything, what we end up with is minus 4 times 3 over 2 lambda, minus 3 times 2 lambda, plus 160 equals 0. And now let's solve for that. We can work this all out, and we get minus 6 lambda plus 160 equals 0. And so that means we have minus 12 lambda plus 160 equals 0. We can solve this to get lambda equals 40 over 3. So now that we have lambda equals 40 over 3, that means y equals 2 times 40 over 3 equals 80 over 3. And then x equals 3/2 times 40 over 3, which is 20. So that means the dimensions that maximize the playpen are y equals 80 over 3 and x equals 20. All right, let's take a look at just one more example in this video. We want to find the maximum of v equals x times y times z, subject to the constraint 6x plus 4y plus 3z minus 24 equals 0. So here we're given this, and this is going to be our f of x, y, z. This will be our g of x, y, z that we're going to make a Lagrange multiplier out of. We're going to put this all in one big equation, and what we're going to end up with is f of x, y, z, lambda equals x, y, z minus lambda times 6x plus 4y plus 3z minus 24. And let's expand that out. We get x, y, z minus 6 lambda x minus 4 lambda y minus 3 lambda z plus 24 lambda. And so now this is just like last time, except we have an extra variable. We have an x, a y, and a z. That just means we take another partial derivative. So let's calculate fx. What we're going to end up with is yz minus 6 lambda. Fy, we're going to get xz minus 4 lambda. Fz, don't forget about z, we're going to get xy minus 3 lambda. And then lastly, f lambda, just like last time, all we're going to get is minus whatever's in here, in these parentheses. So we're going to get minus 6x minus 4y minus 3z plus 24. And we're going to set these all equal to 0. And now we do our best to solve. So here in this function, we can add 6 lambda to both sides and divide. And what we're going to end up with is lambda equals yz over 6. We can plug in for lambda, and we get xz minus 4 times yz over 6 equals 0, which tells us y equals 3 over 2x. And so again, here plugging in for lambda, we get xy minus 3 times yz over 6 equals 0, which is going to tell us z equals 2x. So now that we have all that information, we can make our substitutions in here. We get minus 6x minus 4 times 3 over 2x minus 3 times 2x plus 24 equals 0. Do some simplification. We get minus 6x minus 6x minus 6x plus 24 equals 0. So that means minus 18x plus 24 equals 0. We can subtract 24 from both sides and divide, and that gives us that x is equal to 4 over 3. And now that we know that, we can plug that in here and here. We get z equals 8 over 3 and y equals 2. So that tells us that the maximum occurs at the point 4 over 3, 2, 8 over 3.